Hello and welcome to the course on embedded system design, verification and test. And now we are actually in the third part of the course, that is on embedded system testing. I am Santosh Biswas from IIT Guwahati, and as you have been told in the introductory part of the lecture, I will be telling you on the testing part of embedded systems. So you might have listened in details on design and verification of embedded systems by Professor Arnab Sarkar and Professor Jatin Dekha. Now after doing this initial part, that is how to design an embedded system and how to verify it, finally we have to test it. So basically what happened in the last few series of lectures, you have seen given a specification, whatever models and how they have to be synthesized and how they have to be scheduled, and finally how you design a nice embedded system for a given set of specifications. Then you have seen that as the designs are quite complex in nature, so Professor Dekha has taken you through a journey of what is called verification. How do you formally prove that whatever you have designed or whatever you have intended to design is actually practically correct? Now comes the third part, which is called testing. Now my job will be to take you through the journey of testing of embedded systems. So in this course, if you can look, the course plan is, we are assuming that you have very basic prerequisite of knowing about digital design, some amount of automata theory, etc., and all others we are trying to tell you from the beginning, so that the course become a entirety in itself. So if you see, the first part will give you introduction to digital testing. At the very beginning only I would like to tell you about one assumption. As you have seen, embedded system comprises of some digital hardware, some kind of analog interfaces, some kind of sensors and actuators. But if you start telling in details about how the sensors has to be designed, how they have to be verified, similarly if you talk in details about the actuators or the analog circuits, this course itself will become actually a 3-semester course. It will be very elaborate in nature. So in this course, from the beginning, we are actually taking an assumption that we will be mainly concentrating on the digital part of it. Like whenever we are in this part also, whenever we will be talking about testing, we will concentrate ourselves on the software part and only on the digital processing part. We are not going to cover basically on the analog interfaces or testing on and faults of the sensors and actuators, because those are actually again full courses in itself. So basically what we will try to do, we will try to tell you about digital testing, because our assumption is that for more than 90% of your embedded systems are generally processed using digital circuits. Only we have some kind of, maybe it looks like something like this will be digital hardware, and there will be some kind of analog interfaces here, analog interfaces will be there, and you will have some sensors here, and you may have some actuators here. So basically these sensors and actuators will interface or will take real time readings and it will translate your computation into actions. So they are the job of basically sensors and actuators, and all the processing will happen in digital domain. And these analog interfaces, basically they are analog ADC and DACs, and digital to analog and analog to digital converters. Mainly those will actually convert your digital signals to analog signals so they can be properly interfaced, and also the others, DAC will be there, that is and analog to digital and digital to analog. So such conversions basically will take real world data with the help of sensors and will convert it into in the digital domain, so they can be processed. And again in the another way, if you think that if there will be something some kind of circuits which will take your digital data and convert it into analog, that is called DAC. So and they will be actually interfacing with the actuators, so that the values can be actuated. So your ADC or DAC, there is analog to digital and digital to analog. So they are the main analog circuits which are in embedded systems. So as you can look, basic broad discussion, you could have easily found out that basically most of the processing of embedded software will basically happen in the digital domain. So therefore when we will be talking about our testing, so we will be mainly concentrating on the digital circuits, and we will assume that this testing of sensors, actuators, or testing of the analog circuits, mainly the analog interface circuits like DAC and ADCs, we are not going to study in this course. There are full-fledged courses on analog circuit testing. Analog verification also is now a new subject which is coming up, and in fact testing of sensors and actuators are very large courses in themselves. So we will start this course with introduction to digital testing, then we will tell you how to automatically generate test patterns to test digital circuits, and basically they will be looking at some interesting techniques to test large sequential circuits. That will be the basically introduction part and the prerequisite to know about embedded system testing. Then we will see embedded system hardware testing, that is in this case we will now be diving into depth of testing of digital circuits which will be involved specifically in embedded systems, like software hardware co-validation, fault models, and high level testing of complex circuits. So in this part basically we will try to see if there is a hardware as well as a software, and actually as you have already seen that embedded system basically comprises of hardware and software together. Then we will see what are the different type of fault models which will support such kind of systems, where there is a hardware part, there is a software part, and how different ways you can test those circuits. Basically they are actually called high level fault models and abstract level of testings, which are mainly suited for complex embedded systems. We will be basically looking at such type of circuits in the second module of this lecture. Then we will be also looking at testing of embedded cores. So nowadays if you if you think of embedded processor, there are a lot of cores which are embedded in those, so multi-core processors, system on chip, network on chip. So we will see how basically such embedded cores can be tested. Then we will see that there are if there is large number of embedded cores in a chip, there will be lot of buses and lot of memory involved inside. So we will also have a dedicated lecture to tell you how buses and memories are tested in such kind of system on chips, network on chip or NOCs. So multiple cores, how they are tested, as well as the interconnectivities, how they are tested, and also we will look at basically how memory, which is also a very important component of embedded hardware, will be tested. So that will be basically when we will be discussing in depth of embedded system hardware testing, we will look into these lectures. Then basically we will also look at, then we will look for some advanced fault models, or whenever your circuit starts becoming complex, test model, fault models, testing paradigms, everything becomes more and more difficult and complicated. So in this next module we will see advances in embedded system hardware technique. Like we will see testing of advanced fault model in real time embedded systems. Like embedded systems should also, as we have discussed in depth in design and verification, the embedded systems not only need to provide correct solutions, but they should also be temporally correct. So what do you mean by temporally correct? Means they should be generating the correct data at the correct time. So there are some real time constraints. So we will see what are the different ways of testing such real time constraints, that whether your circuit will be able to meet such real time constraints or not. So that is actually we will be testing for advanced fault models like delay fault models, rise to fall delay, delay to rise, delay to fall, such type of test models which will actually determine whether your circuit will be able to give answers in a predefined deadline will be tested, and how they can be tested we will be covering in advanced fault model testing. Then we will be discussing something called built-in self-test, that is even just a system starts itself. So once you test the circuit after the design, and then you sell it to the customer, then who can guarantee that it will always be correct in future? Nobody can do that. So there is something called built-in self-test, that is every time you switch on your device, now your mobile phone is a handheld device which is an embedded system, your camera is an embedded system, your laptop, the general purpose devices are not embedded systems, but you can just think about your tab. So it's a kind of an embedded system. So any kind of handheld devices generally are embedded systems. So after a system has been fabricated, tested to be properly working, I put it in your system. Now how can you guarantee that every time it will be operating and there will be no fault which can occur basically after the system has been sold to the customer? So say there is something called built-in self-test. Every time a system is started, it will test itself, and if and only if everything is normal, the system will start operating. Else it will tell you that this device is having a problem or this circuit is having a problem, it needs to be replaced. Finally, nowadays avionics, cars, everything has lot of embedded processors, like the automatic cruise control in a car, ABS, anti-locking brake systems. Every domain of avionics, cars, industry have real time or have very critical embedded systems in picture. So if the system is of mission critical or involves human lives, like for example a pacemaker is an embedded system. You think of a diabetic insulin pump, it's an embedded system. So in such cases, even if this system has been tested to be operating properly, sold to the customer, you have built-in self-test that before you start your device it is proper, but still you should always be testing itself. That is called concurrent testing, that is online monitoring, because you have a pacemaker or you have an insulin pump. So everything is properly tested, but after it is delivering insulin say for 20 hours, the pump stops or there is some failure, it delivers more insulin or it delivers less amount of insulin. Who is going to test that in a continuous mode, that whatever what it was supposed to do is working? So in that case there is something called concurrent testing or online testing. That is, even after the system has been deployed, it is doing its normal job, still it is being monitored by a hardware or monitored by a system that throughout its operation it is properly working or not. So that is called concurrent testing for fault tolerance. So we will have 2 dedicated lectures for that, because it is a requirement for lot of embedded systems, because most of the embedded systems are now mission critical or they involve such applications which can have life threatening implications. So we have put 2 lectures on designing of fault tolerant embedded systems. Then finally, there is last module is something interesting, because you know that embedded system means there will be a hardware as well as a software which will be running on it. So we will see how interaction testing happens between hardware and software, because mostly we will see that whenever if you are talking of embedded system testing also, mainly we will be looking at the testing of the hardware, but some amount of emphasis should also be given to understand that if there is a hardware and if there is software which is running on it, which is flexible, so what type of fault modeling and how such systems could be tested. So you have to also look at something called interaction testing between hardware and software. Last but not the least, FPGAs, CPLDs or reprogrammable devices are now occupying a big hardware platform for embedded systems. Instead of having application specific hardware, we are trying to program the FPGAs and we are downloading the soft cores on them. So how to test reprogrammable hardware like FPGAs, CPLDs will also dedicate one lecture for that, because as I told you, nowadays lot of embedded applications are designed and they are dumped into a programmable device, so that you do not have the headache of making an application specific ICs every now and then. So that is also new, the new paradigm shift is going from ASIC to FPGA based implementation for embedded systems. So we will also try to see basically how such systems can be tested. So in broad sense, this is what is our course plan. Now we will start today's lecture, which is basically on introduction to digital testing, and we will also motivate why digital testing is so important and why you should have a prerequisite of digital testing when you are studying basically embedded system testing. So if you look at this slide, this is the, again I think this is a repeat slide, we have been looking at this slide many times in this course. So basically embedded system design, verification and test flow. So basically we have the functional requirements and we have the architecture. Then basically as we have seen, we have a software design part and we have a hardware design part. We bifurcate basically, and modern architecture are also having some kind of internal feedback among them, so that you can switch some of the designs from hardware to software and vice versa. But to keep things simple, we are actually not studying it right now. Then finally there will be an integration, and finally you have to do a test. So this is called the integrated testing. But if you do testing at the last phase, there can be lot of issues, like a bug found over here can be by here and by here, though then you have to do lot of debugging and lot of hard effort increases. So basically what people does, they will also have a test over here and they will also do a test over here. Once they find that both of them basically are operating properly, then basically you can do integration and find and test. Slightly there is a very difference in the terms of testing and verification in embedded in this flow. I will come to that, because when I say test and when I say verification, they are actually something have subtle different meaning when you are studying embedded system design, verification and test. So maybe slightly sounding slightly confusing, but after 2 or 3 slides I feel the confusion will be over. So hardware I say test, and also I can say software as test, and then we can call it as integration testing. Hardware test, testing of the software, and then finally integration, and you do the final test. Then what if you just do not put a test module over here and a test module over here, and if you try to do the testing over here, then it will be very difficult to debug that where the exact issues is. So therefore what people do, there is something like, again just I elaborate it here. So this is your hardware part, and basically you try to test the hardware parts in itself, that is specification, or the hardware design flow is specification, hardware architecture, detailed design, integration and test. This integration is basically only for the hardware components. That is, you decide what part you design in hardware and what part you will be deciding in software, and then basically you have a totally separate flow for the hardware part. You do specs, this is the design part, specification, hardware architecture, detailed design, integration and finally basically test it. So this part actually corresponds to hardware. So that is, you have this one, you are doing it separately, designing, testing separately. The other part basically is your software part. So in this case, let me just remove your, so this is the software, specification, software architecture, design, integration, software part and test. Now there is a subtle difference between test and verification. So here actually I should use the word verification. What is the difference between verification and test? I will take a detailed slide on it later, but for the time being, verification means you have designed a software or a hardware. Then basically whether your design was proper or not, whether you have inserted any or by chance a bug is there inside or not, you want to verify that. So that is actually verification, which has been taught in details by Professor Deka. So you might have noted from there that basically testing a software means basically it's a verification, because the problem is something which you have done by mistake, and so I can use the word verification here. Then what is test? So whenever you are talking of hardware, hardware is basically designed by, say, my modeling, and then we are converting into high level synthesis, then you are making an RTL design, and finally you are making a hardware which is called fabrication. So this hardware, if I say the detailed design, so you are having a model which is done by actually Professor Arnab sir, then finally you have your gate level circuit, and then you finally go for something called fabrication. That is your hardware design. So if I have to verify whether the design of hardware I am doing is fine or not, is actually called your verification. That whatever specification I have taken, whether I have made a proper model or not, whether I am designing it properly from the high level model to an RTL circuit, and then I am translating it into the gate level, whether such things whatever I am doing is proper or not, you want to verify that. So that is actually called verification of design. Now, after the verification of design has been completed, that means you know whatever you wanted to design is proper, how you are translating an RTL circuit to a gate circuit, everything is proper. Now you want to fabricate it. So in fabrication also lot of problems may happen. That is, the idea is that maybe when you are trying to fabricate a thin copper line, there is a break in that copper line. You want to fabricate a transistor, maybe the gate is slightly disconnected. So what can happen is that even though your design was absolutely proper, because you have gone for modeling, you have gone for formal verification, you have got some, you have given some test benches to verify it, every care you have taken before you are doing the design, everything is proper. Now you have sent it for verification. So sent it for fabrication. While fabricating it, the manufacturing industry has inserted some kind of faults in terms of defects. That is, you wanted to fabricate an AND gate, but somehow the output of the AND gate is cut, because there was improper doping of this, this improper doping of copper. Then that is actually a design error, or I should say a fault, which is not because of you. It is because of the fabrication. So if I assume that the design is properly verified and correct, and some faults are getting inserted at the design, at the fabrication part, we want to verify them. That is actually called testing. So there is a certain difference between testing and verification. So when you are saying testing, that is, I have to find out defects which has occurred, not, again quote unquote, not because of the problem with the designer. Designer was absolutely correct, he has given me a proper design, but while fabricating it, some fault has been inserted because of the malpractice, or you can say, defects which is coming in because of the fabrication industry. No fault of the designer. So that if you want to verify, if you want to find out such cases, that is actually called testing. So this I should call actually a test in real sense. And what is verification? Verification is something like this one. So in this case, I should use the word verification. Software part is always verification, because software you are never going to fabricate. So whatever you are writing as a code is going to execute. So there cannot be any defect inserted because of somebody else's fault. If your software is not giving you a proper value, that is the fault of the designer. So we always verify software. So Professor Deka's lectures covered verification part of the software. Now if I say that the hardware design everything is testing, no. In case of hardware part of the embedded system, there is both verification plus test. So again repeating, when you are talking about the software part of embedded system design, everything is verification. Why? Because you are writing the software and there is a hardware platform to execute it. So if there is any problem in the software, it is because of your mistake or the designer's mistake. So if I want to verify that whether I want to establish whether it will execute properly and implement my logic, you have to formally verify it. So there is no kind of testing involved over here. But again I am reiterating because it is certainly confusing, slightly confusing. But when we talk about hardware, there is both test plus verification plus test. I should rather call it the other way, not test verification, it should be verification plus test. Why? Because if I want to design a processor, nobody goes to the industry and put transistors together and make a circuit like that. That nobody does. If you look at VLSI design, verification and test flow, we have a lot of NPTEL lectures on that. So in VLSI design, verification and test flow, what happens? Basically you start designing a circuit in terms of RTL, or there is a model which Professor Arnab sir was telling you. You have to design in terms of specification, that is your or different type of models. Then you will make a hardware architecture, and then there is a detailed design. Detailed design means you are going for high level synthesis, they are going to make an RTL design, and then you are going for a gate level design. You can read any standard VLSI design flow for elaboration on this. All these are basically done with the help of CAD tools. In the software paradigm, that you write a Verilog code, or they are called HDL codes. So you write a hardware definition code for the design, then you synthesize it, then you design a gate level circuit. All these things are done by CAD tools. Every level you have verification stages. Sometimes if you find out that there is certain issues basically which is happening because you have made a mistake in the design, you can reiterate and change in software. So designing a hardware circuit or a VLSI circuit nowadays is not like going to the industry and putting the transistors together. You design in the software level. Finally, when you are satisfied with your design, you send it for fabrication. So before sending it for fabrication, whatever steps you are following is basically verification of your hardware design. After you have sent it for fabrication, there are very high chances that many of the devices are going to have defects. Now, why they are having defects? This is because the fabrication may have problems, and there is lot of, I think as I have given you an example, you might have designed a nice proper AND gate, but it may be getting a cut because doping of copper was not proper. So this fault is happening not because of your error, it is happening because of the problems with the fab industry. So that part is actually called testing. So there is a certain difference between testing and verification. So in this unit basically, that is unit number 3, that is the last unit, we will be mainly talking about testing of embedded system. We are assuming design is proper, software design is proper, but some problems happen in the fabrication stage. How you can find them out? So that is basically the core idea. So I have given lot of time to discuss on this because you have to understand the difference between verification and test in terms of embedded system flow. So this is the embedded system design, verification and test flow, mainly the hardware part. That is why I am emphasizing on hardware. So for example, somebody has told you that this part will be hardware, this part will be software. Hardware part is given to you. So that is your customer requirements. Maybe you want to design a GCD calculator. I want to make an embedded system controller for a microwave oven. The specification has been told to you, that is manual. Then there is something called high level synthesis. You decide that what will be the broad architecture, for how many adders you will put, how many ALUs you will put, how many memory registers you will put. So basic architecture you have to make it. So that is actually called high level synthesis. Then there is something called allocation and binding. You can read any standard course or look at any standard textbook or courses on VLSI design, you can find this out. Then basically there is something called, and always you see verification of RTL with design specification. Design specs are given to you, then you are deciding how many adders, how many multipliers, how many ALU blocks and how they will be scheduled. So whether that one will meet your requirements or not, basically you have to do a verification with it. And again all these are done in CAD tools or at the software level. Even if you are designing the hardware, but you are still writing it in the level of software. Then there is something called RTL design, that is register transfer level design. There is something called logic synthesis, that is you translate into a gates. They are also again done by CAD software. We are not doing it manually. All CAD tools will be available to do it, and they are still at the software level. Again you have to basically go for basically your verification to see that whether the translation happening is equivalent or not. Then there is something called physical layout, floor planning, placement and routing. Now all your gates will be converted into silicon, into transistors, because they have to be placed and finally routed, because at the end whatever you have designed in digital level will be finally fabricated in terms of your transistors. So again you make a plan of it, that I will put my memory over here, I will put my some AND gates over here and so forth. So this part is actually called back end of VLSI design. So we make a plan and then you decide how do you interconnect all this, because large number of transistors will be there. So manually you cannot make interconnection. There are a lot of software or algorithms to do that, and this is also still in the level of CAD. We call it at the back end level. So still now everything is in the level of your transistors, interconnects, etc., but still they are at the level of software. Once this is done, basically finally it goes to the fabrication stage where things will be manufactured at the fab level. That is, however you have told where the transistors will be placed, where the memories will be placed, the fab industry will do the silicon mapping, they will do all kinds of doping, etc., and finally the silicon will be available to you. There is an important part which is called test planning. That is, now what is test? I have told you, if there is some error over here, the errors are getting inserted at the manufacturing, at the fabrication level, not this one, If the errors are actually coming in the fabrication level, then you have to do a test, not a verification, because whatever you have done up to this is correct. Every stage you have verified, every test you have done a simulation based test verification, everything you have done, and we assume that the designer is very knowledgeable, so everything is proper up to here. But certain errors are happening at the level of fabrication. These reasons I will discuss in the next few slides. Assume that because of some problem with the fab industry, some kind of lines are disconnected, you wanted to fabricate an AND gate, one leg is missing, all these things are happening, for which the designer is not the person to be blamed. So you have to verify that. That is, you have to put some inputs, you have to study whether the signals are appearing proper or not. So, you have to do it in the physical level, because when I say that manufacturing, so when are they saying that fabrication, chip to customers. So, now it is no longer at the CAD level, they are physical chips. So, these are actually your physical devices. So, this is no longer at the CAD level. So, whenever you are talking about manufacturing test, it will be no longer a verification, it will be a test, because you will put the device, physical device, you will apply signals over there, and at the output also you will have signals and see whether it matches the golden response. So, this testing is basically called manufacturing testing. In fact, we should always use the word manufacturing test, because test cannot be at the software level. Software level everything is verification, but we generally do not use the word manufacturing test all the time. Basically, you use the word test. But test means the physical device is available to you, you are putting physical signals in, you are getting out physical signals and trying to see everything is proper or not. Then there is something called test planning, because you are doing all these things. Finally, you have to apply something over here to see whether the real physical device which has come out of the fab is operating properly or not. What you will do? How will you apply test patterns? What you are going to expect? So, all these plannings we do beforehand. So, it is actually called test planning. We will see why we cannot put test planning over here. We can also put some test planning over here and drop it. We will see what is the issues with it. The idea is something like, a part is some groups are designing a circuit, and finally you have to manufacturing, and finally this circuit will be available to you. Another group is just monitoring what they are doing, and they are trying to plan when the chip will come to you, what will you do, what type of signals physically you will apply, so that you get to find out whether the circuit which has been fabricated or not is free of defects or not. So, the planning goes beforehand. So, you always try to do the test planning whenever we start the design flow itself. So, this is actually giving you an idea that what do you mean by embedded system hardware design verification and test flow. So, we will be mainly concentrating in this part of the course on the test planning and basically manufacturing test. How do you plan the hardware test, and how do you basically physically test it? This is our main goal. Physical testing means you have to put the device in the tester, apply the signals, get the signals. So, this is some physical activity. Mainly our job will be to do the test planning. Again, I am making a lot of circles over here, because our job will be to plan what will you do. Say for example, somebody gives me 10,000 circuits, physical circuits, and ask me which one is proper and which one is not proper. You have to test it. Then you should have a plan beforehand, that if it comes, what I will apply, what I will measure, and I will tell this is good or this is bad. So, this is actually called test planning. So, I cannot wait till the device is fabricated, it is coming to me, because fabrication will take some amount of time. So, I should also start my plan beforehand, because this part are all at the software level or at the CAD tool. So, I can have the design on my machine also, and I can start doing the plans. So, that is what is actually called the embedded system testing or test planning. Mainly test planning is important, because physical testing means just you put the devices and do the test. So, now we are going into the introductory part of hardware testing for embedded systems. So, why faults will occur? For the first question, you are manufacturing devices, fabrication industries are very sophisticated industry, then ask why a fault will occur. Say for example, I can tell you that some person is repairing or making cycles for me. So, should I ask that out of 100 cycles he will manufacture, 10 cycles will have some problems? Never, it will never happen. So, if I talk about the classical system design like electrical fan, bicycle, scooter, pen, or your physical locks. So, if they manufacture 10,000 locks, maybe only 1 or 2 will have manufacturing defects, which we can throw. But then why we are shouting so much about hardware testing? That means there is really some problem with the fab. So, if I send 10,000 chips to be manufactured, out of 10,000 maybe 500 or around say 40% of the chips may have a problem. 40 may be slightly higher side, but if I say 1,000 chips I have sent to fabricate, maybe 2,000 will have defects. So, there is a good chance that some of the circuits will have defects. Then why? Why such a situation arises? Because such a thing is not very much practical, or you do not see such situations in something called your basically your classical systems like electrical fans, cycles, motors, electrical iron. So, if you manufacture 1,000, maybe 1 or even 0 will have defects. So, why is it happening so much in VLSI? So, we are going to see that one. So, a very important statement which holds in VLSI is called Murphy's law. If anything can go wrong, it will. A very well known statement. That means manufacturing of circuits has certain issues which we look at today, has something that is not very probable of working properly. If you manufacture 100 devices, 20 or 30 may have some issues with it. So, it goes very well with this VLSI fabrication, that if something can go, it will. So what is testing? Testing a system comprises subjecting it to inputs and checking its outputs to verify whether it behaves as per the specifications targeted during design. That is for any system, whether VLSI, whether practical, whether physical, everything, you bring the system or your device, put the inputs, get the outputs and check whether whatever you intended or not is properly functioning or not. In case of digital testing, you will put some digital values and output, you also see digital outputs and match what is intended. Now problem of testing happens because there is something called yield. Yield is nothing but manufactured devices by say correct. How many devices are properly manufactured and total number of manufactured devices. Say 70 devices come out without any faults out of 100 devices. So yield is actually 70%. You will be very surprised that 70% is a very good yield in VLSI. But in case of, if you think of electrical fans, motors, iron, yield is more than 99% because, or even higher, 99.9999%, because such cases there are very real, it is very rare to have some kind of defects in the manufacturing stage. Why is a very interesting story, as we will see. Just before that, let me again tell you what do you mean by difference between verification and test. So what is verification? Verifies the correctness of design. Check if the design meets the specification. So I should say that they are at the CAD tool level or at the software level. I should say the design is at the basically a software level. The design is not at any hardware level. How do you do it? Simulation or formal methods described by Professor Deka. That is, you apply some patterns and see whether it is operating or not, but at the software level, and formal verification is by the formal methods. Performed once prior to manufacture. Of course, once you verify your software is proper, you need not test it, you need not verify it again. But you may have to do it multiple times, but once it is found to be proper, you need not do anything else. So it is done only once prior to manufacturing, and this is required for system reliability anyway. So what is test? Checks the correctness of the manufactured hardware. That is very important. It is at the hardware level. Everything after this stage will only after this. So you have formally verified, or you have verified that whatever designs you have made at the software level bracket is proper. Then you have manufactured it. Then you want to test it. That is actually called testing. The physical manufactured hardware is there. You apply test patterns and see what happens. So verification at the software level, testing is already the hardware level. So we do not use the word explicitly called manufacturing test. It's a two-stage process. Very important. Test generation. CAD tools executed once during the design for ATPG, automatic test pattern generation. So as I told you, there is something called test plan, and second is called test application. Application is very simple. You put the hardware, apply the signals and see the signals. Test patterns are applied to all hardware samples. This is very important. Of course, if you have 10,000 devices which is manufactured, any one of them can have the fault because it is at the problem of the manufacturing stage. But design, once you are doing in the software level, that only is manufactured a number of times expected. So basically verification, therefore they call it done only once. Once the system has been established to be verifiedly proper, it is manufactured. So at the software level, it is done only once for a design. Maybe you have multiple iterations, but only once it is verified to be proper, you need not verify it again. But test means 10,000 samples, everything you have to test, because manufacturing defect can happen in any of them. So they are called all and all hardware samples. So they are very bold lines, all and hardware samples. But again, it's a two-stage process. Why? Because testing also has some kind of a software part in it. That is, how do I plan a test? I have given you a very big circuits of 10 millions of gates. How do you want to test it? Which test patterns you will apply? Can we do it manually? No. So there are a lot of CAD tool solutions where you give the circuits, they will do the test plan with you or help you in making the test plan. So that is actually called the test pattern generation or ATPG. So there are tools which will guide you in generating the test patterns, at which test pattern you will apply, or they will do it in test planning. So that is actually called test generation or test plan, and the second part is called physical testing, which is actually the test I was about to tell you. So testing basically has two parts, test planning and one is test application. Application is simple, all manufactured device one by one it will come, apply physical signals and get it ready to be done. But again, the generation part is, or the test generation or the planning part is a software solution. You take the design and start planning what I have to apply. So a test application is performed on every manufactured device and also it's for the reliability. So I think I have been able to give you an idea of the difference between verification and test. So whenever in this third module, whenever we will be talking about hardware test, so in fact we are talking about two things, test planning and testing the hardware. So testing the hardware we will not look at much, because as I told you, it is just like taking the device, connecting some hardware and measuring the signal. Mainly we will be looking at how to plan the test. And what we will apply? If I have the plan with me, I can easily use a hardware tool or hardware device to apply the test patterns and measure the values. Very, very important is the test planning. So whenever if I still say testing of embedded system, testing of embedded system, hardware testing of embedded system, I will be mainly meaning the test planning of the hardware or the test plans, or how to generate the test plans, or the algorithms to generate the test plans. That will be my main focus when I will be calling testing of hardware systems. Right. Now the question, why hardware testing is so much important, why you are telling about so much emphasizing. So now for the time being, let us forget about the VLSI, let us take a simple electrical iron and let us see what it means. So the basic test of a hardware, basic test, if you see an electrical iron, how do you test it? Is a classical system. Hardware unit means I am talking about a classical system. You plug it into 220 volts AC and see whether it is operating or not. So that is actually a test. Generally we do this is called a functional test, and in fact there is also a partial test. Why? Because whatever amount of hardware, this is what I tell you, whatever, how many number of irons you bring, or the test is done at the shop level, very preliminary level, you put it in the circuit, we switch, put it on, is hitting, it is sold to you. Maybe such a similar test is also done in the industry after manufacturing, but more or less it is not required, because generally what if the yield is very, very high, more than 99.9999%, because whatever you manufacture generally is always subjected to working. Because why? The question is a classical system developed some 300 years ago, and more or less the technology remains same. So maybe slight sophistication has come, you can change the temperature, you can put some oil or some water to make a spray, but otherwise the technique still remains same. Like if there is a coil, it gets heated up and you can use the iron. Like a fan, the technology is more or less remaining similar for last 200 years. There is no change. So we have the manufacturing unit is very, very well versed how to manufacture a fan, how to manufacture an iron. So there is a very, very less probability that any defect will come in between. So therefore when you are talking about classical systems like your fan, cycle, motorcycle, bike or scooters, generally the test part is very, very preliminary, because as a manufacturer I know very well what is my job, and the functionality more or less remains same over the last 50 or 60 years. So that is the key role, that classical industries testing is important, but not very, very important as in the case of VLSI. Okay, so if the basically if your electrical iron is bit costly, so we will also see the test for safety, that all the parts of the irons are grounded, there is auto off facility for overheating, so you can increase some amount of test. So you can see testing things, whenever things start becoming complex, testing complexity also increases. If it is a simple electrical iron just heating, so the test is simple, put it into the AC, on it and your job is done. But if it is a more expensive one, so you have to go for all exposed parts are grounded, auto overheating off. Even we can go for more detailed testing like heat when the power is on, glow of the LED, then temperature matching with specification like wood, silk, cotton, etc. So more sophisticated a device becomes, more sophisticated the testing becomes. But still this technology was still known more than 50 years ago. So and technology more or remains same. So the yield is very, very high. So testing is not that important in such cases, because if I devise 10,000 chips, 10,000 irons, maybe only one or two will have a defect, and easily it can be very easily verified by the shopkeeper. Then if the electrical iron is becoming more and more sophisticated and you need a performance guarantee, etc., then you have to see for the power consumption, like if it's a 5-star AC. So you have to also measure the power requirements. So you have to also see the power consumption specification. Then time required to reach the desired temperature when the range is changed in the regulator. So I have to give you a performance. But in the iron such things are never required. Then I change from silk to woolen. So and I put to do it. So I will generally give certain amount of time. There is not ever a hard real deadline that it should happen by this time. But assume that such things were there, then the performance testing will also come into picture. So in fact there is something called basic functionality, detailed testing like safety, basically then performance. So more a device becomes sophisticated, more amount of testing has to be done. Another philosophy you can see over here is basically if the device functionally remains preliminary, which is not changed over years, then testing basically remains a very simple phenomenon. Why? Because we know how to manufacture those simple devices over 50 to 60 years or even 100 years. So yield will be very, very high in this case. But if you want to fabricate or design something very new which is changing every day, then you are prone to make errors even in your manufacturing stage. So therefore in such cases you have to always test all the devices. Again, certain stray parameters, as I am saying, for the mechanical, for the iron test. Say for example, I want to test the manufacturing parameters, that if I throw the, or if I drop the iron from a certain distance, whether it will break or not. So I mean, nobody will do such a test in a iron, but I am just trying to give you the example that testing can be infinite in nature. This test space is infinite. It can be a simple function test to a huge test even for a simple iron. It all depends what is the time you have, what is the cost of the device, and what is the reliability required for this. It will tell you what to test and what not to test depending on all the parameters. Now I will basically come to your circuits. Why it is so much required? I want to test this simple NAND gate. So what will you do? You will give me all these 4 combinations, and the output of the NAND gate, we know that for all combinations except 1 1, the answer will be a 0. So basically you can say that I want to do the test. Now compared to iron or a cycle or a gadget, or a mechanical gadget whose design is not changed over the last 100 years, NAND gate, you can think that it has been designed last 30 years or so in the range of VLSI. But if you look at the VLSI, we first had simple integration, then we had medium scale integration, then large scale integration, ultra large scale integration, and now we have a very large scale integration, or even now, but we are not using more terms above VLSI, but now we have extremely sophisticated device where millions of transistors are dumped into a single IC like NOCs and SOCs. So maybe what I will tell you what happens. So when we have medium scale integration, so basically what happens in fabrication, generally you have to lay out, make copper wires, maybe then you will have a gap, then we will put another copper wire, then maybe we will put a via over here. So there is a certain gap in between these two. So using your mechanical dopers, we actually fabricate these lines, maybe silicon, copper, vias, and we put it on this, and there is a gap. Now what happens if I make the gap quite large? Very good, there will be no problems, and if I say that I make these lines very thick, and if the gaps are high, then you can understand that the chances of failures will be less, that the manufacturing failures, because I will lay once, then I lay 2, so there can be any discontinuity. And if I make the gap quite large, there will be no chances of any short in between. But now if I do this, your chip size will become very large. So if you have a very large IC, if you look at device physics, manufacturing a very large chip in a single die has lot of physical problems. You cannot do that. I don't want to go into depth, but just take from me, take quote unquote, that I cannot have a very big single die. It has to be smaller ones. Now in a smaller die, if I make this line thick, if I make this gap high, then what will happen? There will be restriction in the number of devices going into it. So maybe I can do 10,000 like this. But if I make these lines very thin, and I have a very thin gap in between these two, then what is going to happen? Then maybe I will be able to put more and more devices in this single chip. So what more chips devices mean? More functionality. More functionality means your device will have more kind of functionalities and more wide range of specification. So your market will be higher. Like for example, you know that Nokia, I am just giving an example, you should not go by vendor names basically, but if you see Nokia had a very good robust mobile phone, but it went down in the market because some other companies like Samsung, Apple and all other industries started giving more functionalities. So more functionalities means I have to put more devices inside a chip. So the market will go, or even we also try to go and purchase devices which have more functionalities at lower cost. So by lower cost means I have to try to put more number of chips, or sorry, more number of transistors in a single die, so that I can give you more functionalities. But again, as I told you, die size cannot be increased because of some physical limitations. So what I will try to do, I will try to make a very thin line, and I will try to also make the gap very thin. So nowadays from 5 micron design, today we are in the nanometer design, 95, 65 nanometers. Now if you try to do it, what is the problem? If you make a very thin line doping, it may have some kind of gaps in between, and if I try to make very thin lines, there can be shorts. The idea is that the more thinner you want to make a line and more less gaps you want to keep, you are going to have defects like shorts and opens. But still I have to go by that, because if I give you a very reliable circuit, but if the functionality is very less, nobody will try to purchase it. Rather what people will like to do is that people will try to take a circuit with more number of functionalities. But can I sell a circuit like this which is having shorts and opens? No. So what I will do, I will manufacture 1000 devices, test all of them, maybe 200 having some defects, I will throw them out, 800s I will sell at a higher cost, like this one is correct, this one is wrong, same thin and thin difference. I will sell those 800 at a higher price, and 200 which are having defects, I will throw them out of the picture. So in such cases what is going to happen? Such cases your market will be raised, because you are giving more functionalities. So the economics is driving us. So the economics is driving you to a situation where you have to fabricate more number of devices in a single die. So I need very thin lines and very thin gaps in between, so that I can put more devices and I can put more functionalities and sell into the market. More defects, obviously, because making a thin line and little gaps may have to open and shorts. How will I escape from the market? I will test all of them. Whatever will have been defects, even if these 20%, 30%, no problem. I will throw the defective pieces out of the bin, and I will sell only the good ones to the customer with an increased price. Still, you are going to make a profit. So this is market driven, not a engineering driven stuff. So market drives me to make such kind of sophisticated devices. They have a term called painting a thin line with thick brush. They call it this way, painting a thin line with a thick brush. So of course you are going to make error. So what is a brush here? Brush is actually your fabricating equipment. Now of course, today I am manufacturing 65 micron. After some time I have to go to even lower 35 micron. But maybe I am just having 2 months, 2 years to change this from a higher micron to a lower micron. That is, the gap will be less, lines will be thinner. So I require some time to put R&D and do lot of innovations to make such a complicated fabrication machine. But the time given to me is less. 2 years may not be enough time to do it. So my machine is also half completed in design. So what happens? I will make some kind of errors like open, shorts, but still I want to go by that, because I want to have my market where I will throw out the elements which are defective and sell the correct ones with a higher price, and will hold the market. So this is driven test, or such kind of manufacturing trend in VLSI is a market driven phenomena or economic driven phenomena. For example, say 65 nanometer had lot of defects today, but after 10 years, maybe if I am pursuing the 65 nanometer technology, then I will have a very robust manufacturing unit by that time, where there will be very less defects. But 10 years down the line, 65 nanometer nobody will purchase from you. There will be further lower technologies coming into picture. So the time you are giving me to make a manufacturing unit is not high, so that I can give you a very reliable designs. So because I am also a designer of my manufacturing unit, so I will tell you that the prime pressure you have given me, I will give you a 65 nanometer or 35 nanometer design, but there will be lot of defects. So defects may be as high as 30% or 40%. Still it is not a problem. You test all the devices, whichever are having defects you throw them out and sell only the proper ones to your customers. Of course you have to note at this point, I cannot sell a defective part to a customer. So this will be a gross problem. So say 10,000 devices has been fabricated, I have to test all of them physically. So maybe out of them 200 or 2000 are having defects, 800 are normal. So this normal 800 I will sell to the customer with a higher price, but I have put lot of functionalities. I will go by this trend rather than not going by a system where the micron is less and the technology is built old, but out of 10,000, 9,999 devices are proper. I will not go by this trend, because that will make me lose out in the market. As that story I have been telling you, you know that about Nokia and high advanced devices with lot of functionalities like other mobile phones like Samsung, all the other companies like your basically Mi, Xiaomi and all those phones which have more functionalities, but somehow if you might have used all of them, reliability is slightly less. But again, as I told you, so this part is very important. You cannot send a defective parts to a customer. You have to test it, throw it, and basically sell at a higher price. So that is, and you might have appreciated by now that I know how to build a cycle over 200 years. I know how to build a electrical iron over 70 years. Technology has not much changed. So therefore, there is a very less chance of having physical errors at the manufacturing stage devices in classical literature. Right. So that is why testing of hardware is a very important area in case of any kind of embedded system design or any kind, so for that nature of any kind of VLSI industry. Extremely important that you have to always go for, you have to think a lot about testing, and which is not the case in case of classical design. Okay, with this motivation, let us start about your basics of testing. So in this case, you have to give all these 4 variables as inputs, and if everything is proper, your circuit is operating fine. Now, so that is actually the basic functionality testing. Now, in case of embedded system, a very important part is deadline. That if some example I am giving something like this, and then maybe so basically, and then again I have a circuit like this, so the output may be falling like this. Both 1 1, the answer will be from 1 to 0. So if after this, after you have applied this both, what is the time taken to make for this fall? That is actually called real time. So you cannot give a very high time for the AND gate to respond. If the time taken by the AND gate to respond, even if the answer is correct, there is a lot of delay, means your embedded system will not be able to give the solution in real time. So that is actually called the delay time, delay test. From 0 to 1, that is time taken by the gate to rise from 0 to 1, and similarly there will be a fall test from 1 to 0. So basically what you can do, take these two inputs as 1, you change one value to 0, so output will be changing from 0 to 1, and you can find out what is the rise time. So the pattern will be, you will have a 1 1 over here, and then quickly you switch V2 from 1 to 0 1 to 0, and output will be changing like this, and the delay you have to measure. So there are many other ways of doing the same thing, which is written over here. So any of them you can apply, and you want to see whether the rise is proper or not. You can also say that I have to do it exhaustive testing, because I want to ensure you that in all the probability, or in all chances of combination of inputs, what will be the rise time, and I have to ensure that it rise within the predefined threshold, so that my embedded system can give the answers in a real time. So this is called the delay test, rise test and fall test. There is also something called fan out test. How many gates I can connect to this? There is something called a fan out. So you have to guarantee that I can drive 10 gates out, I can give 20 gates, or I can do only 4 gates as the output of it, or I can drive like that. So all this information I have to provide, and how can I do that? So I may have designed it to drive say 4 AND gates, but it is not driving it properly, maybe because of it is not able to drive properly, there is some delay faults are happening, or some other types of faults are happening. So you have to also go for testing of all this. I call the testing of the fan out capability. Then something called power. So I am not going into the details of all these tests right now. Whenever required in course of time, we will be giving. I am just, as this is the introductory lecture, so we are trying to put you in basically what are the basic stuff required for testing and the motivation we are building. So that is called fan out testing. Maybe there is something called power. Nowadays all the embedded systems are powered by batteries. So you have to always determine, but what is the power consumption of this gate? So basically there is something called static power, and there is something called dynamic power. Static power is measuring the power when the output of the circuit is not switching. Dynamic power is when the inputs and outputs are switching. So you have to measure the power, and you have to find out whether it is meeting the predefined requirement or not. Otherwise, if it is overshooting, then whatever guarantee you have said that the mobile phone or device will work for 10 hours at the non-talk time, 3 hours at the talk time. So you may not be able to meet these guarantees. So therefore you have to also do power consumption test. There is something called threshold test. Threshold test means basically like what voltage you are considering as 1 and what voltage that you are considering as 0. So maybe you are considering as 0.3 to 1 as your 1, and maybe 0.7 to 0.4, say maybe 4.7 to 5 volts as logic 1. So whether it is meeting those thresholds or not. So those testings also you have to do, that if the output should be expected as 1, so the output voltage is between 4.7 and 5. Similarly, if the output of the gate is 0, it should be within these voltage levels. Then there is something called testing at extreme temperatures. Your embedded system, the unit may be in the car engine, so the engine temperature may become high. So within that high temperature also, whether all the parameters are happening properly or not, that is actually called testing at extreme condition. Temperature is one of them. So you can also test at that level. Now I can again make this list very, very large, infinitely large I can make, just like the electrical iron. Similarly for the AND gate you can do it. Of course, electrical iron, the test whatever I have told you, nobody will do anything extra than just putting it into the power and see whether operating or not, and maybe slightly will check the thermostat. But in case of these gates, at least we have to do functionality, we have to do delay, we have to do fan out, we have to do power and threshold. Maybe if we can drop the extreme level. These things we can drop, because the more tests you put, more price you have to pay. But the number of tests you have to do for an AND gate or an electronic circuit will be much higher than a classical system. And I can make the list as high as possible if you have time and if you have money. Because finally you have to also gain profit. Nobody will purchase a mobile phone with 10 lakh rupees, which is say that you will always guarantee to operate for next 10 years. Nobody likes a device or an embedded system like that. So you have to make a reasonable amount of test to give a reasonable performance at a reasonable cost. One interesting thing I should tell you is that basically embedded system industry mainly runs by your test economics or the value and money and the market, rather than giving a very, very reliable engineering solution which may not be feasible in the market. It is not only about embedded system, for most of the engineering disciplines. Now finally, as I told you, maybe all the silicon, all the NAND, any kind of gates will be finally manufactured in terms of transistors. So you can also say that apart from the gate level, I will also test at the transistor levels. So this is the CMOS implementation of the NAND gate. I am not going to go to the details, but now I can go for the testing at each of the transistor levels. That is output characters, IDS by means drain source current by the volt drain to source, transfer characteristics, threshold voltage characteristics. So all these tests are cases are basically at the level of transistors. Now we have to go internally and we have to tap out such points and do test at this. More reliability will have, but more sophistication it will be. Finally, this is actually the layout of the NAND gate. Now people will, as I was saying, that this may be a copper, this is a copper, this may be a copper, this may be silicon, this may be a via, so metal, all the names you can see, these are poly. So now I want to say, I want to find out whether this metal is properly laid out or not. I can do the testing, you require a prober to do it. Whether I want to see whether these contacts are properly there or not, I have to do some kind of probe based test. Means testing a NAND gate itself will take years and years, and manufacturing one NAND gate cost maybe millions of dollars. So that is what I am trying to tell you, is that even for the circuits, even the circuits have lot of issues in case of manufacturing and defects, still you cannot go to at this level for each of the gates. You will be actually, there will be no monetary benefit to go at this level. Then basically at what point we should stop, so that we can give you a reliable solution. Generally we stop basically, as I told you, we go for functionality test, we go for delay test, basically we go for power consumption test. Mainly these three states we do it elaborately. Functionality, of course you have to do, delay because embedded systems has to, delay deadlines has to be met, and basically power consumption. Mostly such tests we have to do for all the circuits at a certain level of, giving a certain level of rigor, because below that you may be selling off a defective part to a customer. Other things we should do, even at this level we should do, but the problem is that you will not be able to have any monetary gain out of it. So that is actually called the optimal quality of test. So given a digital logic gate, what tests are to be performed to ensure an acceptable quality of product at a reasonable price? So as I told you an example, functionality, delay and power. So basically it should be, accuracy should be very high, maybe 99% above, and embedded system digital testing is not test the digital circuits comprising of NAND gates. Digital test, this is a very interesting statement. Digital testing is not testing digital circuits. Rather, digital testing is defined as testing a digital circuit to verify that it performs the specific logic functions and at proper time plus power. I should add the word power. That means if you say that I want to test a digital circuit, so digital circuit testing means comprising all, this one, transistor level, and finally at the fabrication level, at the device level. So that will actually say that I am testing a digital circuit, because digital circuit finally is at the transistor level. But in fact that, as I told you, is practically impossible. So rather what is testing here means you take a gate like this and you say that whether it is giving the proper outputs at the proper time. So that was actually the classical definition of test. Like digital circuit is defined as testing a digital circuit to verify that it performs the specific logic functions in proper time. This is temporal correctness. Plus we are nowadays adding power, because in case of embedded system power is also becoming a huge constraint. So this is actually, I think this slide is telling you an idea about what is testing, how rigorous it can be, but for a practical economical feasibility, how much you should apply for an embedded system hardware. So this slides basically compares the classical system testing versus VLSI testing. I have been telling you so many times, but just let us look at it. Hardware testing, that is VLSI. Technology matures and faults tends to decrease, and a new technology evolves for a lower submicron design. As I told you, now 65 is a good technology. Give me 10 years, I will give a very robust manufacturing unit of 65 nanometer. But by the 10 years, another much complicated fabrication technology will be coming into picture, and there you have lot of defects, because I am not ready with that manufacturing unit as is. But in terms of classical systems, basic technology is matured and well tested. So therefore in classical systems faults rarely occur, and therefore testing is not a very major challenge in classical systems. So in case of, so there is a slightly, I am just sorry, this should be coming over here and this should be coming over here, slightly a mistake. So basically in case of classical systems, they are diagnosed and repaired. I mean this statement should come over here and this statement should go over here. So but in case of, so in case of classical system, we all know that basically they are diagnosed and repaired. If there is a problem in the electric iron, you can repair it. But in case of hardware, they are deemed as defective and scrapped and not at all repaired. So this part actually corresponds to hardware, slight mistake in manufacturing table, and this part corresponds to classical. right? So this was the classical. So basically in classical you are diagnosed and repaired, but in case of VLSI we just throw them out because there is no way of repairing it. Hardware testing yield is low, the reason already told. Here yield is almost 100%. Very expensive equipments and specialized manpower is required to the hardware testing, because you have to put voltage, current, you have to open up the chip sometimes, put probers, so it's a very expensive procedure. Classical system, very simple, even the roadside vendor can do it for you. Here all samples has to be tested, because if somebody tells within 100 some 10 chips will be faulty or 20 chips will be faulty, you have to test all of them. But in case of classical, as the reliability is very high, you just do some random sample testing, maybe 10,000 units are going out, you just take 1 and 2, because you know that mainly if there is no gross abnormality in the supply chain, everything will be proper. So test managements are required in design, here is rarely. Now what? This is actually called test plan, which will be mainly reading in this class, that is test plan, sorry. This is also the test plan but not required. So test plan means you have to make lot of arrangements to test the circuit, because it is very sophisticated. A circuit will have 10,000 gates. From the simple NAND gate example, you could have find out that testing is not very simple. But if it's a very huge circuit with tens of thousands of gates, then you have to plan beforehand what you will apply, how will you apply, what will you measure, so that you can do the testing in a reasonable amount of time. But in case of classical system, we rarely need to do any planning, because we know that whatever we are generating without any gross abnormality, everything will be proper. So the test is very simple. So we never think about the planning itself. But in case of hardware, things is very different. So I think I am able to give you an idea that why is VLSI testing or embedded system testing is more involved or more required or more important than compared to any classical system of engineering. And in this part also I have told you, I think I have been able to tell you the difference between verification and test in case of embedded systems. With this motivation, basically next class we will try to give you the algorithm of test planning, because whenever you think about testing, again I am repeating it, in case of VLSI or embedded system, testing means putting the hardware, connecting and deriving the values and getting it. But what really means motivates us as computer engineers or electrical engineers are, how will you plan your test, that given a big circuit, how will you make the efficient test patterns so that you can do the test efficiently and a very less amount of time. Like I have told you that I want correct functionality, correct time and power. Other things I am not going to measure, because if I do it, cost will be very high and reliability will slightly increase. So how do I have such insights or how test plans? That is actually the job of the test engineers. So in this module, basically we will be learning about test planning of embedded systems. So with this we come to the end of this introductory lecture. In tomorrow's lecture, what we are going to do is that we are going to take real examples of circuits and we will find out algorithms how to test the circuits. Okay, thank you.